Hello everybody, welcome back to this CCNA routing and switching video series brought to you by ABY Design and Tech. In this video, we will be exploring the concepts behind IP addressing. So to begin with, what is a IP address? An IP address is just a logical address which is assigned to every device on your network. The reason why it's logical, because it's only bound to your device whilst it's connected to that network. If you were to move, let's say, from your home network to your corporate network, you were to move your laptop, chances are you would be assigned a different IP address. And IP addressing allows logical grouping because it allows you to group your devices into networks based on what network you connect to. And the reason why is defined as logical grouping because you're only part of that group whilst you're part of that network. So whilst you are connected to that network, you will be part of a group. As soon as you move to another network, you'll be part of a different group. Now, anything connected to a network, anything at all, will have to use IP addresses for communication. Now, I know what you're thinking, Abda, how come when I use my web browser and I wanted to watch these awesome ABY Design and Tech videos, all I did was go to my web browser and browse to youtube.com? The answer is because we have a protocol called DNS, which stands for the main name system protocol. So the way that DNS works is that DNS is used to resolve host names into IP addresses. You see, YouTube.com, that is just a name given to a server. The analogy that I'm going to use is, imagine I'm holding a party. Everybody says to you, okay, you can go to this awesome party. It's being held at Abdi's house. Now, chances are that Abdi's house doesn't actually mean anything to you. It doesn't tell you any more information about how to actually get to my house. If you wanted to get to my house, you would have to find, okay, what is the address of Abdi's house? His street address, his postcode, etc. Essentially, that's what DNS does, is that DNS just tells you, okay, this server you want to access called youtube.com, which has the YouTube website. This is what the actual IP address is of that server, so now you can reach it. So as an example, let's say Bob, he wants to access youtube.com because he wants to watch this awesome video series. He knows the host name of youtube.com, but he doesn't know the IP address. So he's like, wait a minute, I can just use my DNS server to find out the IP address of youtube.com, to find out the IP address of that server. So now I'm going to send a DNS request to my DNS server. He sends the DNS request to the server, essentially saying, hello DNS server, I want to know the IP address of youtube.com. The DNS server responds, and he's like, hello Bob, youtube.com actually has the IP address 55.3.3.22. Now, Bob can speak directly to youtube.com and essentially say, hello 55.3.3.22, I would like to retrieve the homepage for youtube.com. Now, if you want to see the actual DNS process in action, you can just open a command prompt on your Windows machine, on your Linux machine. It's going to be a terminal, and you can just simply type in the command nslookup and then the host name of the website. So this could be google.com, facebook.com, youtube.com, etc. Essentially, what that will return that this server, which has the name youtube.com, actually has the IP address 172.217.169.78. That's the process your computer follows when you type that in on your web browser. And the reason why we use host names when we browse to different websites is because it's easier for us humans to understand. Imagine if for every website you had to type in an IP address. Chances are you're not going to remember what the IP address is, but it's very easy to remember what a host name is or what a domain name is. You can easily recognize and remember youtube.com, facebook.com, google.com. If you had to type in the IP address, chances are that you would probably forget. Now that we understand that IP addresses are used for all communication across a network, let's start to have a look at the actual an in-depth look at IP addresses. So before we even continue, we need to understand binary. Essentially, the reason being because computers communicate in binary, and yes, computers do communicate IP addresses in binary. Now, I know what you're thinking, but Abda, the IP addresses we've been looking at have just been decimal numbers. Well, there are two ways to represent an IP address, in its binary format and its decimal format. Of course, we use the decimal format as human beings because it's easier for us to understand. But it's very important that when a computer is communicating or looking at IP addresses, it looks at the IP address in binary format. Things such as subnetting, defining the network part of the IP address, is all done in binary. So we need to understand decimal and binary and how to convert between both. So let's have a look at binary first. Binary is just a number which is expressed in a base 2 numerical system. Essentially, it uses two numbers, a 0 or a 1. Now, again, before we actually dive deep into binary, let's have a look at the decimal number system. The reason being, because everybody understands the decimal number system, because that's what we use throughout high school and throughout our educational career. So decimal numbers, they are expressed using a base 10 numerical system, and the numbers for each column can range from a 1 through a 9. So if you think about it, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we have to introduce a new column, which is going to be a 10. So a 10, if you think about the number 10, it's made up of a 1 on the left, a 0 on the right. Then we have 11, 12, 13, 14, all the way up to 99. Then we have to move over one more column, and then we have a 100. Now, it's important to realize that each column actually increases by a power of 10, by a factor of 10. So as an example, 10 to the power of 0 is 1, 10 to the power of 1 is 10, 10 to the power of 2 is 100, 10 to the power of 3 is 1000. Now, to understand this, let's actually look at a decimal number. So in this case, let's have a look at decimal number 356. Now, this is made up of 300 plus 50 plus 6. And if we look at the actual number itself, there are 3 columns. There's a column for a 6, a column for a 5, a column for a 3. Now let's move from the leftmost column or the third column all the way to the rightmost column or the first column. Now the third column has a 3, but it's not actually a 3. What that column is used to represent is used to represent a 300. And essentially this is 3 times 10 times 10. The second column is a 5, but it's not actually a 5. It's used to represent 50, which is 5 times 10. The first column is actually a 6, and is used to represent 6 times 1. And so I've included this chart over here on the right, and essentially this is how we would break down decimal numbers. Now we don't usually see decimal numbers like this because we don't need to. We understand how the decimal numbering system works. We understand that each column within a decimal number can have a value from 1 through 9, and we start with units, tens, hundreds, thousands, 10,000s, etc. So if we break this down, all we're doing with this number is the rightmost column is 10 to the power of 0. Whenever you start any numbering, it's always going to be to the power of 0. Anything to the power of 0 is 1. Then we move to the middle column, 10 to the power of 1, which is 10. 10 to the power of 2, which is 100. So if we break down this number, it's 6 times 1, which is 6. 5 times 10, which is 50. 3 times 100, which is 300. So in this case, we have 300 plus 50 plus 6, which equals a decimal number 356. So like I said, we're not used to seeing decimal numbers like this, but it's very important that we understand how the decimal number system works before we move over to binary, because binary essentially uses the same principles. So moving on to binary uses the same principles, but instead we use base 2. So instead of each column of a number going up by a power of 10, now we're going up by powers of 2. So each column from right to left increases by a power of 2. So as example, let's dissect binary number 1010. That's made up of 4 digits, so in this case 4 columns. The rightmost column is going to be 2 to the power of 0, which is 1. The second column is going to be 2 to the power of 1, which is 2. 2 to the power of 2, which is 4. And then 2 to the power of 3, which is 8. Now, binary number 1010, what does that mean? What does that equal, or what is the equivalent in decimal? And the way that we worked it out is simple. Is the same way how we worked out what the decimal number 356 is. In this case, we do 0 times 1 plus 1 times 2 plus 0 times 4 plus 1 times 8, which is 10. So binary 1010 is actually equal to decimal 10. So all we're literally doing is we're taking the value, the 0 or the 1 over here, and we're multiplying it by the value of the base 2 within that column. So in this case, 0 times 1 is 0, 1 times 2 is 2, 0 times 4 is 0, 1 times 8 is 8. So as an example, decimal 1 is just going to be 1. Decimal 0 is going to be 0. Decimal 2, however, is going to be 1, 0. Decimal 3 would be 1, 1. Decimal 4 would be 1, 0, 0, etc. And so it's literally as simple as that. Whenever you see a binary number, if you want to convert it to decimal, all you would do is look, okay, how many digits have I got? Have I got 7 binary numbers, 8 binary numbers? Now, going from right to left, I know that each number represents is going to be separated into a column, and that's going to be a power of 2. So obviously from right to left, we start with 2 to the power of 0, 2 to the power of 1, to the power of 2, etc. Once we have the power of 2 numbers written down, then we just say, okay, what is 1 multiplied by 8, or 0 multiplied by 4, etc., as we have seen in this example. Now, what does this have to do with IP addresses? Well, IP addresses themselves are made up of 32 binary bits, and these 32 binary bits are divided into 4 sections of 8 bits, and each section is called an octet. The reason why it's called an octet is because it's got 8 bits. And essentially each octet or each section is separated by a period, which is a dot. And IP addresses are in binary format, and computers communicate using binary format. So as example, 32 binary bits. If you wanted to, you could pause the video and count right now. There'll be 32 bits. And essentially each octet is separate. So the IP address is split up into 4 sections, which are each called octets, and they're made up of 8 bits. And just so that you know, each section can have a decimal value of 0 through 255. And the reason being is because with 8 binary bits, we can make any decimal number from 0 through 255. So again, I know what you've been saying. The IP addresses we've been looking at so far have not been in binary format, they've been in decimal format. The reason being is because there are actually 2 ways to represent IP addresses. Dotted decimal notation, which is what us humans see. So whenever we configure an IP address on a network interface card, whether it be Windows or Linux or Mac, we are going to be configuring using the dotted decimal format or binary format. Now binary format is what the computers say. Now the reason why we have to understand binary format is because when we start doing things like subnetting, or when we have to identify which part of the IP address represents our network part, which part of the IP address represents our host part, that's all done in binary. So let's start to have a look at this. So like I said before, is that we use IP addresses in decimal number for each octet because it's easier for us as human beings to understand. However, to understand why each octet can only have a value from 0 through 255, let's break up one octet into its binary equivalent. So obviously we know that an IP address is broken up into 4 sections called octets, and each octet has 8 binary bits. This means that there are 8 binary columns per octet. So as example, moving from left to right, the rightmost binary bit for that column, for that octet will be 2 to the power of 0, then 2 to the power of 1, which is 2, 2 to the power of 2, which is 4, 2 to the power of 3, which is 8, 2 to the power of 4, which is 16, 2 to the power of 5, which is 32, 2 to the power of 6, which is 64, 2 to the power of 7, which is 128. And what that means is that we can use any one of these values within the octet in binary to make up a decimal value from 0 to 255. So to see an example of this, let's actually break down the binary IP address that we saw earlier in this section in this video. So let's break it down octet by octet. So the first octet is 1100000000. Now, to convert that number into decimal, we write out our chart, okay? So we know that there are 8 binary bits. We start with 2 to the power of 0, work our way all the way up. So now we have a 1 for the 128 and the 1 for the 64. So all we literally do is 1 times 128, 1 times 64, add those together, and that gives us 192. Now if you go to the second octet, which is 10101000, we put a 1 in the leftmost binary bit, which is going to be a 128. We put a 0, 64, 132, 0, 16, 18, 04, 02, 01. So now all we do is add 128 plus 32 plus 8 plus which gives us 168. Now let's have a look at the third octet. 11001000. That's going to be 128 plus 64 plus 8, which gives us 200. Now we look at the last octet, which is going to be 00001010. That gives us 0001010, which gives us 10. So as you can see, to actually convert from binary to decimal is actually very easy. All we do is we will always write out this chart, and the chart will always be the same because each octet has 8 binary bits. And each octet, moving from right to left, can have one of 8 values, either a 1, 2, 4, 8, 16, 30, 64, 128, because we're going up in powers of 2. And then all we do is that we just write our binary number, so moving from left to right, 1, 1, etc. And then all we do is that wherever there's a 1, we add those numbers together. So in this case, there's a 1 for 128, 1 for 64. I'm going to add those 2 numbers together, which give me 192. And the same with the second octet. Wherever there's a 1, I'm going to add those numbers together. So 128 plus 32 plus 8 gives me my decimal equivalent, which is 168. Now, I know what you're thinking. What if I want to convert from decimal to binary? Then all we do is we still write out this chart. Okay, so we're also going to be writing out this chart. So again, we did this per octet. Let's say that we wanted to convert 192 into its binary equivalent. And so all we literally think now is when we're doing from decimal to binary conversions, we'll write this chart and say, oh, okay, moving from left to right, what numbers, so based on the numbers I have available, what numbers do I need to add together to make up 192? In this case, I know it's going to be 128 by 64. Or if I wanted to make up the number of 10, again, I write out this chart, and moving from left to right is important. You always move from left to right. I think to myself, okay, what numbers do I need to add together to make 10? In this case, it's going to be 8 and 2, and so the binary equivalent of decimal 10 is going to be 1010, or the binary equivalent of 200 is going to be 11001000. It's literally as simple as that. So again, this magic that we've done, all we've done is just convert binary into decimal. And like I said, to convert from decimal into binary, we write out that chart again, and we just move from left to right thinking, oh, okay, what numbers, based on the numbers I have available, do I need to add together to make that decimal number? And as a network engineer, you will be moving from binary to decimal very, very often. Again, we use this because of subnetting and to find out the network port of our IP address. And again, we need to understand how to convert from binary into decimal. And luckily for you guys, we can just use this chart. So this chart, we could just use this whenever we want to convert any IP address into its binary equivalent. Again, we go from one octet to another octet to another octet. So first we're going to start with the first octet, and let's say we want to convert that into its binary equivalent. We just write out this chart. So to remember, guys, okay, 8 bits per octet. We start with 2 to the power of 0, which is 1, 2 to the power of 2, which is 2, 2 to the power 1, which is 2, 2 to the power of 2, which is 4, 2 to the power of 3, which is 8, 2 to the power of 4, 16, etc, etc. And then once we have written out a chart, we move from left to right and think to ourselves, if I want to make up that that decimal number, which numbers do I need to add to make up that decimal number? And we move from left to right, and if we need that number, then we put a 1. If we don't need the number, then we put a 0. Simple as that. And so like I said, this is important because the IP address itself is broken up into 2 parts, a network part and a host part, and essentially we need to convert from decimal to binary to see which bits represent the network part and which bits represent the host part. So the network part represents the group that you're a part of, and every device within that network has to have the same network part, because just like in real life, we group things together based on something they all have in similar. The host part is a unique ID for your device within that group. So now I know what you're thinking. Okay, I know that an IP address is broken up into a network part and a host part, but how do we identify which part of the IP address represents the network part? Obviously, I've been telling you guys that we have to use binary conversions. Well, whenever you configure an IP address, you always configure another setting that is called a subnet mask. And essentially, your subnet mask is 32 bits in length. Is broken up into 4 sections called octets. And it's the subnet mask that identifies which part of the IP address represents the network part. Now, 32 bits in length, 4 sections called octets, that sounds similar, right? However, the main difference, and this is the biggest difference, is that for each octet of the subnet mask, we can't have any value from 0 through to 255. So, like with the IP address, we can have any value. So we can have like 17, 18, 30, 101, 201. Those can be the decimal values for any octet of the IP address. However, with the subnet mask, each octet just can't have any value, any decimal value. It can only have 1 of 8 decimal values. So now let's have a look at the difference between an IP address and a subnet mask. So we'll understand the difference once we actually have a look in binary. So the main difference between a subnet mask and a IP address is that for each octet of the subnet mask is made up of a contiguous string of binary ones. So as example, let's have a look at this example. If we had a binary octet and this was the value of the binary octet, then that is correct. We could have that binary value for an octet of an IP address. However, if we were to have this value for a subnet mask, this binary value for an octet of the subnet mask, that is wrong. The reason being is because with a subnet mask, we can't mix binary zeros and binary ones. Essentially, with a subnet mask, each octet is made up of a contiguous string of binary ones. So we have binary ones on the left, as soon as we see a binary 0, then that means that the rest of the binary bits for that subnet mask have to be a 0. And so because we can only have ones on the left and zeros on the right, that means that the value of each subnet mask octet can only be one of 8 decimal values. So as an example, if an octet were to have the binary value of 1 and then 7 zeros, that means that the subnet mask value in decimal would be 128. If we were to have 2 consecutive ones and 6 zeros, that means that subnet mask value for the octet would be 192. If we were to have 3 consecutive binary ones and 5 consecutive binary zeros, that means that subnet mask value would be 224 in decimal. If we were to have 4 binary ones and 4 binary zeros, that means that subnet mask octet would have a decimal value of 240, 5 binary ones, 3 binary zeros, 248, 6 binary ones, 2 binary zeros, a value of 252, 7 binary ones, 1 binary zero, a value of 254, and if all the octets and if all the binary bits for the octet were set to 1, that means that subnet mask value for the octet in decimal would be 255. And so as you can see, we could only have one of 8 different values for each subnet mask octet. And subnet mask can be presented in 3 different formats. We could have dotted decimal notation, which is like its representation in decimal value, and we can have the representation in binary. Now, the representation in binary is what we just saw in the previous slide. And we can also have prefix format. So prefix format is represented as a / followed by a number. And all that number denotes is the number of consecutive binary ones in that subnet mask. So as example, a /16 would say we've got 16 binary ones and 16 binary zeros. A /24 means that we have a contiguous set of 24 binary ones. And so just to make this clear, guys, is that because the subnet mask is a string of consecutive binary ones, if as soon as we see a 0 bit in the subnet mask, we cannot have a binary one after that. Okay, we cannot have a binary one after that. So when we look at the subnet mask, is made up of 32 bits. It's going to be all ones on the left. As soon as we see the first 0 bit, we cannot have another 1 bit after that, because essentially that is the 0 bit which identifies the host part, and it's the 1 bit which identifies the network part. And so let's have a look at some examples of this. As example, imagine that we have assigned the IP address 192.168.200.10 to our host within our network, and we've given it the subnet mask 255.255.255.0. Now, breaking this down into binary, this is the binary equivalent of the subnet mask. This is the binary of the IP address. This is the binary equivalent of the subnet mask. Now, as you can see, 255.255.255 is made up of 8 ones followed by 8 ones followed by 8 ones. So that means that the first 3 digits of the IP address represent the network part, and the last digit of the IP address represents the host part. That means that for any devices in this network, the first 3 digits have to be exactly the same. The first 3 digits have to be 192.168.200. And the prefix mask will be a /24, because if you count from left to right, we have 24 binary ones. Moving on to example 2, imagine that we were in our network, we configured a host with the IP address 172.16.255.1 with a subnet mask of 255.255.0.0. Now, if we were to break each octet into its binary equivalent, 255 is made up of 8 ones, 255 is made up of all 8 ones, and then 0, 0. Okay, so for any of you eagle-eyed viewers, you'll realize I made a slight mistake with the subnet mask and binary, so that's been changed. So we know obviously 0, 0 means that we have 8 zeros and 8 zeros. So if we now break this down, because the first 16 bits are binary ones, that means that the first 16 bits of the IP address represent the network part. So in this case, the first 2 digits. The last 16 bits represent the host part. So in this case, any device in this network, the IP address has to begin with 172.16 because that identifies the network they're a part of. The last 2 digits can be any number from 0 through 255 because that represents that unique host within that network. And the prefix mask for this subnet mask would be a /16 because if you go from left to right, we have 16 binary ones. Now moving on to example 3, which is a bit more tricky. So example 3, we have assigned our host the IP address 10.22.31.45 and we've given it the subnet mask 255.248.0.0. So this is what we have to do, okay? So we are going to convert each of the subnet mask octets to its binary equivalent. So obviously the first number should be easy because we know that whenever we see a 255, that means that there are all binary ones for the octet. Now, when we want to convert 248, to make up that number, we know that with the subnet mask, it's got all ones on the left and zeros on the right. So it follows a set of consecutive ones. So as you can see, we have 1, 1, all ones here, followed by all ones here. As soon as we see a 0, we don't see a 1 in the subnet mask again. So 248, its binary equivalent is 1, 1, 1, 1, 1, 0, 0, 0. So this means that the first 8 plus 5, 13 bits of the IP address represent the network part. And the last 19 bits of the IP address represent the host part. And that this is where it gets a bit tricky. This is why we need to use binary when we're subnetting. Because in the previous examples, we saw subnet mask of 255 or 255.0.0 or 255.255.255.0. Whenever we see a 255 in a subnet mask, that means that entire octet has to be the same for every device within that IP address. Now, whenever we see anything other than a 255 in a subnet mask octet, that means that only a certain number of bits have to be the same in the IP address for a device to be considered in the same network. So as example, we've assigned the IP address 10.22.31.45 to a device within our network. This gets a bit tricky because we could have another device which is in the same network as our original device, but now with the IP address 10.17.1.1. And the easiest way to see this is breaking down this second octet. So what this subnet mask says is that for any device in our network, the first 5 bits of the second octet have to have the value 00010. As long as their binary value of the first 5 bits in the second octet of the IP address is 00010, that means they're in the same network as us. As example, 10.17. If we break 17 into its binary equivalent, we have 00010.001. So as you can see, the first 5 binary bits are equal to 00010, which puts us in the same network as 10.22.31.45. However, an IP address such as 10.25.1.1 is not in the same network as us. The reason being is because if we break that 25 into its binary equivalent, we have 000110001. As you can see, the first 5, so we have 000, that's brilliant. We have a 1, but then we have a 1 for bit number 5 as well. So because there's a 1 in bit number 5, it doesn't meet our requirements that the first 5 bits have to have the binary value 00010. And so this is why it's important to understand binary, because it's when we're using subnet masks which don't have a 255 in the octet that we have to use binary to understand essentially the range of IP addresses and what bits of that IP address have to match for that device to be considered in the same network as us. Now, as a rule of thumb, whenever we see a 255 in the subnet mask, that means that the corresponding octet in the IP address has to be the exact same value. So obviously, if you go back to our previous example, we saw this, where the first octet in the subnet mask is 255. That means that all devices have to begin with a 10 in their first octet. Now, if you don't see a 255 in the subnet mask octet, that means that we need to find out how many bits in the octet need to be the same by converting the octet into its binary equivalents. As example, if we were to convert 200 into its binary equivalent, and if we were to convert 248 into its binary equivalent, we know that 248 is made up of 1, 2, 3, 4, 5 bits of consecutive ones. So we know that for any device to be considered in the same network as a device with the IP address 192.168.200.15, the first 5 bits of the third octet have to have the value 11001. That means a device with the IP address 201 in the third octet would still be within our network, because the first 5 bits of that third decimal number will still be 11001. And now it's important to understand that within our network there are 2 special addresses which cannot be used for host. This is the first IP address of each network, which is called the network address, and is essentially used to identify that group. Then we have the last IP address, which is the broadcast address, and that is used to send IP packets to all users within that network. And so just to make this clear, those IP addresses cannot be assigned out to any devices, because those are reserved to identify the network, identify that this is the group, and essentially it's used in a router's routing table to mean that to reach all devices within this group, within this network, you can use this row. Then we have the broadcast address, which is the last IP address within that network, which is used to identify how we can send a broadcast message or broadcast packet to all devices within that network. Now, to work out these addresses, we can use a simple rule. The network address, it has all its host bits are set to 0. To find out the broadcast address, we just set all host bits to 1. And the first usable IP address is +1 to the network address. The last usable IP address is -1 to the broadcast address. So now going back to examples, let's see how we can work this out. So as example, again, we're using the subnet mask 255.205.250. That means that the first 3 octets have to be the same for a device to be considered in the same network as a device with the IP address 192.168.200.10. Now, to find out the network address, all we do is convert these last 8 bits to binary 0. So the network address is going to be 192.168.200.1. Now the first usable IP address is going to be one more than that. The first usable IP address is going to be 192.168.200.1. To find out the broadcast address, we just convert all bits in the host part of an IP address to all ones. So in this case, the broadcast IP address is going to be 192.168.200.255. Again, this is used to send an IP packet to all devices within our network. To find out the last usable IP address, we just subtract a decimal 1 from this value. So the last IP address that we can assign out to any host is going to be 192.168.200.254. So now moving on to our second example, we have a subnet mask 255.255.0.0. Its prefix almost going to be a /16, because if we were to convert that subnet mask into its binary equivalent, we would have a set of 16 consecutive binary ones. The IP address is 172.16.255.1. So now to work out the network address, all we do is we know that with a subnet mask of 255.255, we have 16 binary ones followed by 16 binary zeros. The binary zeros represent the host part of our IP address. So we know that the last 2 octets represent the host part. We just convert those octets to all zeros. So the network address is going to be 172.16.0.0, which represents our network, which represents our group. To find out the first usable IP address, we just add a decimal 1 to that number. The first usable IP address for any device on this network is going to be 172.16.0.1, and that's the first IP address that we can assign out to our host. The broadcast address, we do the opposite. For the bits which represent the host part of our IP address, we just convert those bits all to once. So the broadcast address is going to be 172.16.255.255. Again, to find out the last usable IP address, we just subtract a decimal 1 from the last octet, and that's going to be 172.16.255.254. So that IP address we can assign out to a host within our network. Now moving on to our third example, again, which is using a bit more of a tricky subnet mask. So obviously we know that with a subnet mask of 255.248, the first 13 bits represent the network part, the last 19 bits represent the host part. Okay, now to find the network address, we just convert all of those last 19 bits that represent the host part to 0. So that means the network address is going to be 10.16.0.0. The first usable IP address is going to be 10.16.0.1, because we just add a 1 on. The broadcast address, we do the opposite. The last 19 bits which represent the subnet mask, we just convert to binary 1. So in this case, the broadcast address is going to be 10.23.255.255. That can't be used, that's only used for broadcast messages. To find the last usable IP address that we can assign out to our host, we just subtract 1, which gives us the last usable IP address of 10.23.255.254. And so by finding out the network address and the broadcast address, we can actually find out the range of IP addresses that can be used within our network. And guys, so just to clear up some confusion, like I said before, a subnet mask can have 1 of 8 values per octet. However, what we can't do is we can't start mixing 1s and 0s together. So as an example, this subnet mask up here. Now it looks like it's a correct subnet mask because it's got the one of a decimal values for each octet. However, it's actually not a correct subnet mask, and the reason being is if we were to convert this to as a binary equivalent, we are actually mixing ones and zeros. So as you can see, we have we have all ones over here, followed by zeros, followed by one. That's not a correct subnet mask because the ones all have to be on the left, the zeros all have to be on the right. This second subnet mask would actually be a correct subnet mask because we have all ones, a set of contiguous ones followed by a set of zeros. And it's important to understand it's the zeros in the subnet mask which identify the host part of the IP address. It's the ones in the subnet mask which identify the network part. As another example, this third subnet mask value would be incorrect, even though it's got the correct values for each octet. The reason why it's wrong is because, again, we're mixing ones and zeros. As soon as we see a zero, the bits after that should all be zero. We should not see any one bit after that. That's what makes this subnet mask incorrect. And as another example, this fourth subnet mask is correct because we have all ones on the left and all zeros on the right. So usually, whenever we see a subnet mask octet with a value of something other than 255, that means that is where the binary ones end. So as you can see here, the third octet has a value other than 255. That means that it's got one binary one, and then the rest of the bits in that octet are going to be binary zeros, and essentially the rest of the bits after that should all be binary zeros. So we have reached the end of this video, and just to recap, we've looked at IP addresses, how we can convert from decimal to binary, why it's so important to understand why we need to be able to read IP addresses in binary, and how it comes into hand when we want a subnet or when we want to use a subnet mask to identify the network part and the host part of our IP address. Please join me next time where we will go through the different classes of IP address, the different types of IP addresses. Like I will say, if you enjoy this content and want to see more like it, please subscribe to my channel. Please share this video so we can get high quality IT training free of charge to the masses. Thank you very much.